All right, as we look at molar mass, add up all the weights. If you can do that, you can do a tremendous amount of homework questions and a lot of conversion factors of more complicated homework questions, and those are eventually exam questions. So as you look at molar mass, just think periodic table. And when you see carbon, think what is its weight on the periodic table, what is oxygen's weight on the periodic table, and there's two of those, so you're going to have to double that. So as you look at CO2, notice we're stealing those numbers. 12.01, straight off the periodic table. 15.99, that's basically the 16 that we see on a periodic table in the classroom. And notice that we have 2 oxygens, so we're adding up 2 oxygens in the total molar mass. So using this process of just adding up from the periodic table can get you a lot of answers very quickly, because we can assume that if we're adding up grams, we're counting 602 trillion atoms without even counting them. So when we say mole, that tells us that we're using Avogadro's number of atoms. So be careful. If it says molar mass, that's the mass of 1 mole. It's the mass of 602 trillion atoms. And that's where we can safely use grams. In more complicated formulas, remember to multiply across. So here we have 3 nitrogens, check. We have 3 times 4, which is 12 hydrogens, check. We have just 1 phosphorus, check. And then we have 4 O's, check. So by using those multiples, then we're just straight back to the periodic table. Adding up the numbers, hitting equals, and getting those answers very quickly. But again, this is grams, so it's per mole. That means per 602 trillion atoms. So remember, if we're using moles, it's based on Avogadro's number. That's just our dozen. It's a chemistry's dozen, so to speak. One thing nice about molar mass is we can use it to convert grams and moles. Specifically, that's going to be helpful if we're converting ingredients in grams to products in grams, or vice versa. So notice here we can have any conversion, right side up or upside down. So the ability to flip these is just if you have some number of moles, you're going to use this one. If you have some number of grams, you're going to use this one. Any piece of information we take from the periodic table or from a balanced chemical equation pretty soon, we can use as a conversion. And that's why we're practicing conversions in pretty much every chapter on exam 5. Hopefully that repetition, that muscle memory of conversions will pay off in the end. A lot of times students don't know how to set up problems. So if you see a problem like this, notice there's only one number. If there's only one number, we have to put that number out front. So 250 grams. This is grams of water specifically, so we're going to get rid of whatever we have, and we have grams of water, so that goes on the bottom. Then we go to the periodic table, and we do H plus O, and that's per 1 molar, 602 trillion water molecules is implied in this situation. So we have about 1.01, 1.01, and about 16. So we get about 18.02. So when we divide 250 by 18.02, we're going to get that answer. So again, they have a little bit more sig figs in their mass. It just depends on what periodic table you use, whether you can get away with that or not. But here we're getting 13.88 moles. If 1 mole is 18 grams, we're just saying how many 18 grams are in 250. And it's almost 14 in this situation. If instead we have 13.8 moles, that's the only number we have. The only number we have, we're going to put out front. If this is moles of water, now instead we're going to get rid of moles of water. We know in 1 mole we can use the periodic table, and that's just H plus O. And there's that 18.02 grams of water. So this will give us grams of water in the end. So we're just going to take 13.88 and multiply by 18.02, and we're going to get back that answer that we saw a moment ago of 250. So notice any conversion we can use right side up or upside down. Most important though is moles have to cancel here, but grams had to cancel in the previous problem. So moles are friend. Moles is the only way to get from grams to molecules. There is no way to go from grams to molecules directly. You have to go through moles. That's at least 2 conversions. And we'll see that briefly in some homework problems and so forth. One of the things that's important, and we'll see this in lab coming up, is theoretical yield. Theoretical yield is a lot like taking an exam. Theoretically, you can get 100 questions correct, and on the last test, several students were very close. Theoretical yield in chemistry is very similar. We can calculate how much product we can make, and then as we make it, we'll see if we're successful in that venture or not. This is really no different than baking a cake. You think you can make 2 cakes for somebody's birthday party, but then when you drop a few eggs on the ground or you spill the flour or something of that nature, then the ability to make 2 full cakes is no longer possible without going to the store and getting more. So chemistry has the same issue. You can spill things from your beaker. You can, accidentally pour things out, tip things over. So theoretical yield is how much you could make with no mistakes. And we know that's probably not going to be reality. Actual yield is what you actually make. So if we go back to that cheesecake idea and we have, 5 eggs per cheesecake, but we drop 1 egg on the ground, we can't make a full cheesecake anymore. We can make a smaller version of the cheesecake instead. So because it's easy to make mistakes, both in chemistry and in life, what you actually get is kind of like the actual grade on the test. So if you only got 70 questions out of 100, that means you made 30 mistakes, and that happens. So as we look at percent yield, that's just like the percentage on an exam. You take your actual score, you divide it by your theoretical score, which would have been 100 questions, and then you times it by 100 to get that percentage. So if you got 70 questions correct out of 100 questions total, times 100, that's a 70%. So again, these ideas aren't brand new. Percentage ideas are something you were probably taught in middle school. We're just applying it to chemistry because when we make products, sometimes we don't make as much as we calculated. So as you look at percent yield, notice they give you 2 numbers in this situation. So notice here it says 225 is isolated. Possible was 255. So that's where you take your isolated grams and you divide it by the calculated possible grams. That's no different than saying you have 225 questions correct out of 255 questions. Once you times that by 100, you'll get percent yield. So in this case, not too bad, about 88%, which means they didn't make too many mistakes. As we look at balanced equations, that's just one more way to get moles. So we already know that we can get moles from the periodic table to deal with grams, and now we know we can get moles from Avogadro's number to deal with atoms or molecules or even formula units if we're dealing with metals and nonmetals. So as we look at a balanced chemical equation here, notice this is a 1 to 1 to 2. So we're using those ratios of saying there's 2 HIs for every 1. That's just comparing this number to that one. We can also say that there's 1 to 2 just by flipping it over. We can also say that there's 2 to 1 HI. That's just comparing this number to that one. And then we can flip it over, right? We can also compare ingredient to ingredient. So we can compare 1 to 1. And whether you flip that up or not doesn't change the math, but it will change the unit cancellation. So any of those coefficients can be compared to one another to help us convert from ingredient to ingredient or ingredient to product. It's also true that we can use, instead of coefficients, we can use subscripts. Subscripts are a great way to represent how many atoms are in a particular molecule. So notice here we have a formula of H2. So all we're really saying is that there's 2 H atoms for every 1 H2 molecule. There's 2 iodine atoms for every 1 iodine molecule. There's imaginarily 1 hydrogen atom per HI molecule. And there's 1 imaginary, subscript, implied subscript. There's 1 I atom in every HI molecule. So it's a little bit rare to use those, but it is something that you'll see briefly, using subscripts instead of coefficients. Coefficients being a whole lot more useful and a whole lot more common in some of our homework and exam questions. So as we look at a recipe, just think eggs, sugar, cheesecake, right? It's very similar. Just looks a little creepier because it's chemistry. So as you're looking at a conversion between aluminum and oxygen, that's really just a conversion between ingredient and ingredient. This tells us every time we use 4 moles of aluminum, we're going to have to use 3 moles of oxygen. So notice we're just stealing this coefficient here and then stealing this coefficient here. And remember, you can also flip these upside down if we need to change them. That's fine too. It just depends on what we start with. If we start with moles of oxygen, we're good. If we start with moles of aluminum, we're going to have to flip this over. Down here, they say, what's the conversion between oxygen molecules and oxygen atoms? Well, we don't need the equation at all for that. We just need to realize that oxygen molecule has 2 oxygen atoms. So for every 1 mole of O2, we have 2 moles of oxygen. So what's important to realize here is oxygen, the diatomic molecule, here oxygen is an atom. So we're basically just using that subscript and we're using it that as a conversion. And again, you can flip this right side up or upside down. So any conversion can be used right side up or upside down. That's the take-home message. As we see a lot of this chapter unfolding, all those numbers are now conversions. And all those numbers on the periodic table at the very bottom with all those decimals are conversions. And then we have fancy Avogadro's number on top of it that's a conversion. So if we have a mass of H2 required to make 10 grams of HI. So this is kind of like you're going to a drive-through. This happens to be a chemistry drive-through. Somebody orders 10 grams. A lot of students, when they get to this chapter, they don't know how to set up the problem, but you only have one number given in a lot of these problems. You take your one and only number and you put it out front. This is where it's very important to label. So here we're going to label HI. And the first thing we're going to do is get rid of HI, no different than the last chapter with the metric system. In order to continue, we're going to have to go back a few slides and get the balanced equation. That's H2 plus I2 gives you 2HI. Second step, though, after we've canceled grams of HI, here we can go H plus I on the periodic table and 1 mole of HI. They want mass of H2. So eventually we're going to get to grams of H2 way down here. That tells us that we're going to have a conversion that has grams of H2 on top eventually. And that's just going to be H plus H. So that's about 2.02. Down here we have 1.01 plus about 126.9. So that's about 127.9 0.91. And again, that's just taking those weights on the bottom of the periodic table. This is, again, per 1 mole of H2. And notice we have a problem. HI does not cancel with H2. But HI cancels with HI. So if we take this down and say moles of HI, we can just as soon take this up and say moles of H2. Mole-to-mole ratios either come in two forms, whether it's coefficients, which we have some, or subscripts, which we have some. Subscripts are only used when we're dealing with atoms. We're dealing with grams, so we're going to be dealing with moles, and that's a 1:1:2 ratio. So we're going to take this 1 and bring it all the way over. Then we're going to take this 2 and bring it all the way down. So we're going to take 10 grams and divide it by 127.91, divide by 2, multiply by 2.02, and then it equals. Notice the major features of this setup, though, is if you have grams of A, some random ingredient or product, you're going to have to get rid of grams of A. And that's going to be 1 mole of A as you deal with that from the periodic table. Then you're going to have to go to the periodic table and get grams by adding up all the atoms of A. So again, that's the periodic table. As moles of A cancel, just as grams of A cancel, moles of A cancel, so that goes on the bottom. And what we're going to see in this chapter also is as we get to grams of B, we're going to have grams of B on top. That's going to come from the periodic table. That's per 1 mole of B, and that's going to have to cancel up top with moles of B. So a funny story about moles is notice your little mole kind of runs across the top of the problem, gets scared, he digs his little hole, and then he runs across the bottom. That mole to mole to mole to mole ratio, top, and bottom, super popular for a lot of homework questions in this chapter, the next chapter, and our final chapter of this semester. So recognize this pattern. This pattern can give you a lot of answers for a lot of the questions coming up. So notice in this situation, if we want to model that based on what we just saw, here's A, grams of A cancel. Here's moles of A cancels. And then as we got to B, we have grams of B. So grams of B out here, that's the surviving unit. This is moles of B, and that's canceling with moles of B. So notice that pattern fits perfectly to what we'd expect. And the answer here about 0.07. Let's try one more problem and think about, in this case, subscripts instead of coefficients because we have no balanced chemical equation here. So again, we only have one number, so let's put out 10.7 grams oxygen. First step is to get rid of grams of oxygen. Anytime we're dealing with grams, we're dealing with the periodic table. In this case, that's about 16 plus 16, so it's about 32 almost perfectly. That's per 1 mole of oxygen. We're going to have to get rid of moles of oxygen. So notice cancel, cancel. Very common. Notice they want oxygen atoms. Oxygen atoms is what we're after. So in our last conversion, oxygen atoms should be left over. Well, we know in 1 mole of anything, oxygen included, Avogadro's number is the number of atoms. Now we just need moles of oxygen to cancel. And uniquely here, we don't have coefficients. But we can say that in 1 mole of O2, we have 2 moles of oxygen atoms. So here's where we're using subscripts instead of coefficients because we don't have a balanced chemical equation. More importantly, notice that pattern before we show you the answer. This is just A, canceling with A. And this is moles of A, canceling with moles of A. And this is just B, canceling with B, so that you're left with B in the end. And that's exactly that same pattern that we expected, and we're going to expect in a lot more chapters. So here we're using molar mass in our first conversion, we're using subscripts in our middle conversion, we're using Avogadro's number, which is really all 3 definitions that we have in this chapter, aside to the coefficient definition. So when in doubt, convert to moles. If you're not using moles and the definitions of moles, you're in trouble because they should be in just about every problem that you're doing in this homework. We'll catch you with the next video.